Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous session, we talked about the type of PLL and the order of PLLs, and we told that the loop filter is a block which decides between different PLL types and order. So, today we will look at examples of PLL with different types and order. So, we are going examples of PLLs with a different type and order, and the reason to choose different type and order will become clearer as we go through our analysis. Okay, the different types and order. So, let me just recall that PLL which we have been using. We had a mixer based phase error detector, followed by the loop filter which has a transfer function loop filter of S, followed by the VCO which has a transfer function k VCO over S, and this feeds back. Okay. The input and output are voltages, sinusoidal voltages. In our case, we will treat right now V in as sine of omega in t and V out as cosine of omega out t. Okay. We drew the small signal model of this particular PLL, and the small signal model of the PLL is shown here. You have the phase error detector with input phase and feedback phase, which is phi in feedback phase. The gain of the phase error detector is k PD, followed by loop filter LF of S, which is followed by VCO with gain k VCO over S. This is the small signal model of the PLL. This is phi out. Here you are going to get phi error. Output of the phase error detector is voltage. We call this as V error. Output of the loop filter is control voltage, that is VC. Now, where will this type and order of PLL matter? It will matter when we apply any change in phase or any change in frequency of the PLL, and we want to find whether this PLL will remain in lock or it will go out of lock, or what will happen. So, one standard method of a closed loop feedback system is, let us say you have this closed loop PLL, it is closed loop in nature, which that is why I am calling it as a closed loop, and it is in steady state. That means, for at time t equal to 0, let us say that the rate of change of phase error is equal to 0. That is how the PLL is in steady state, and your omega in is equal to omega out. So, you have a PLL which is in steady state. Now, you apply change in input phase or input frequency, and if the PLL still remains in lock, which means that at t equal to, let us say, 0 plus, I apply a change in the input phase, which is that delta phi in is equal to delta phi in 0 times u of t. This is just one kind of change which is applied to the PLL, and then we give it enough time such that all the transients die out, and we look at the PLL in steady state, which is after enough time we would like to find what is the phase error in steady state. Why we look at phase error in steady state? Because in steady state or as time t tends to infinity, the phase error should not change if the PLL is locked. So, this is the thing which we are looking at. If phase error as t tends to infinity is some fixed value, okay, then the PLL will be considered that it is in log. If this value tends to infinity, then it is like the phase error increases with respect to time, it is not logged. We would like to find out this particular phase error for different kinds of inputs, which will depend on the type of loop filter which we choose. So, let us begin with an example. We will consider many examples. First, the loop gain of the PLL is given by Lg of S. Loop gain of the PLL, you see that this is the loop and we are considering when you apply a change what comes back, that is the loop gain. This loop gain is equal to Kpd times Lf of S times KVCO over S. Okay. When we applied a change at input change is phase step, which here we will call as input phase step, this is what we apply. Okay. So, delta phi in is given as delta phi in 0 times u of t. In frequency domain, on Laplace domain, you have delta phi in of S given by delta phi in 0 by S. Okay, this is for the step input. So, for this particular case, our error at infinity is equal to, this is going to be equal to limit S tends to 0, S times phase error of S. In the previous session, we also find what is this phase error of S? This is going to be S times 1 by 1 plus loop gain times phi in of S. How? Well, you know from this particular loop that phase error is equal in frequency domain, phase error of S is equal to phase in of S minus phase out of S. Okay. So, you might be seeing here that I am using phase error of S or phase in of S and delta phase in of S interchangeably. Okay. So, that is like the small change which I am applying. So, phi out of S is equal to loop gain by 1 plus loop gain times phi in of S. So, from here this expression is clear. Okay. Now, this value, this particular value is equal to S tends to 0, 1 by 1 plus loop gain. So, your loop gain is Kpd times KVCO over S times loop filter of S into delta phi in 0 by S. Okay. So, this goes off, right, and you substitute here S equal to 0. So, when I am going to substitute here S equal to 0, let me rewrite in a different form. So, I am having S divided by S plus Kpd KVCO times loop filter of S. So, what you are going to get here is 0. So, you applied a phase input, okay, a phase step input, and in a steady state you found that the error in a steady state is going to be 0. What it means? It means that if I apply a delta phi in 0 here, after some time I will see a change in delta phi out, which is same as delta phi in 0. So, that delta phi error becomes 0. That is what you have. Okay. and every PLL we know is type 1 PLL. So, here the loop filter of S, you can see it will only be a problem when loop filter of S is loop filter of 0 is equal to 0, right. Then you have a 0 by 0 which is not defined, which is not the case also. So, for type 1 PLL, I can write limit t tends to infinity, phase error of t for phase input is equal to 0 for type 1 PLL. Okay, does not matter what order we have here, right. Now, with this phase step, let us see if I apply another change, which is frequency step. When we apply a frequency step to the PLL, so here I am going to apply a frequency step where delta omega in is equal to delta omega in 0 times u of t, step at time instant t equal to 0. We know that delta phase in for applied frequency step is equal to delta omega in times dt integration 0 to t. Now, in Laplace domain, this frequency step relates to phase ramp as given by delta omega in of 0 divided by s square. We would like to find what is the phase error as t tends to infinity for the frequency step. This is going to be s tends to 0 s times delta phase error of s, which is equal to limit s tends to 0 s times phase error of s is equal to delta phi in of s here divided by 1 by 1 plus loop gain. I will substitute the parameters for 1 by 1 plus loop gain directly here. This s times delta phi in of s is nothing but delta omega in of 0 divided by s square into s times s plus kpd kvco times loop filter of s. Okay. Now, as you see that I can cancel s, both of these s, and what I have here is s tends to 0 delta omega in 0 divided by s plus kpd kvco times loop filter of s, which in turn is going to give me delta omega in 0 divided by kpd times kvco into loop filter of 0. This is my steady state error in the PLL. So far I have not discussed that what is loop filter of 0, but you can see very well here that for type 1 PLL, loop filter of 0 is equal to 1, where let me just remind you that loop filter of S we have used for type 1 PLL is 1 plus S tau 1. Okay. For type 2 PLL, one of the examples which we saw earlier. So, let me first write the loop filter expression. This was equal to 1 plus S tau p divided by S tau I. This is our type 2 PLL with 2 integrators. Okay. What is loop filter of 0? Loop filter of 0 is actually equal to infinity. If this is the case, then for frequency step, a steady state phase error, where I am writing phi error, let us say steady state is termed as limit t tends to infinity phi error of t. Okay. For type 1 PLL, our steady state error is equal to type 1 phi error steady state is equal to delta omega in whatever the frequency step you provided by kpd into kvco times 1. Okay. for type 2 PLL, what you see is phi error of steady state, because loop filter of 0 goes to infinity is equal to 0. Okay. So, this is interesting that for the same for the PLL, you have input and output frequencies locked, and when you apply a simple phase step, you see that both in type 1 and type 2 PLL your error will be equal to 0, but when you apply frequency step for type 1 PLL there is an steady state error, but for type 2 PLL the steady state error is equal to 0. Okay. But keep one thing in mind, that this particular value phi error steady state which you see here, right, this does not take into account the large signal, or you can say the actual voltage signal at each of these nodes. It does not take into account, it is only for a small signal modeling. So, why is this important? Well, we have seen earlier that in this the model for type 1 which we are using, just to remind you, in the model type 1 which we are using, V of error is k PD times phase error. Okay. But actually if you remember, V error is equal to half of sine times the phase error. We have seen this before, I am just repeating it because we are discussing with respect to types and orders. So, in this model there is no restriction on phi error, okay. There is no restriction at all on phi error, but if you look at it, there is, no matter what your phi error you are going to have, there is a restriction on V error. Okay. Here if you see, if phi error is, if delta omega in 0 is large, phi error will also be large. If I increase delta this one, phi error will increase, and it appears that your PLL will always remain in log. Whereas, in this particular whereas actually what you see is, even if phi error increases, your V error is bounded. So, if V error does not increase, the V control voltage will not increase and you will not be able to get the desired frequency change. But for a small changes which limits our, which are limited by this, your modeling here that phi error steady state will be valid. Okay. In case of type 2 PLL, it does not matter, because in a steady state you are going to have the phase error of 0. You will acquire all the frequency with the help of the integrator in the, another integrator in the loop. Well, this is interesting that for type 1 and type 2 PLL we are able to get that. Now comes another question, what happens? Okay, we applied frequency step. Now, if I am going to apply frequency ramp, okay. So, what do you mean by frequency ramp? That delta omega in of t is increasing at a fixed rate. I am calling that rate as delta omega in 0 times t. Okay. So, this is like you can say this is an integral of delta omega in 0 times dt. Okay. So, for frequency ramp, the transfer function in Laplace domain for the change in the frequency is going to be delta omega in 0 divided by s square, and for the corresponding change in the frequency, the change in the phase is going to be delta omega in of 0 divided by s cube. Now, for the desired frequency change of frequency ramp, the change in phase is given by this. I need to find out that whether the PLL will remain in lock or not, which means I need to find out what is the steady state error value. Well, same principle, nothing changes here. Phi error of steady state is limit t tends to infinity phase error of t. That is what I need to find. This is equal to s tends to 0 using the final value theorem into phi error of s, which in turn is equal to s tends to 0 delta omega in 0 by s cube times 1 by 1 plus loop gain, that is what we have been using all the while. So, this is equal to s tends to 0 s times delta omega in 0 by s cube into s divided by s plus kpd times k VCO into loop filter of s. Okay. So, you see I can just subtract or remove all these things from here. What I get here is delta omega in 0 divided by s square plus s times kpd k VCO times loop filter of s. Okay. So, I have to substitute s equal to 0. So, I will just rewrite it as where with the remaining important terms omega n of 0. So, this is term will anyways be 0. So, this I will not substitute because the evaluation depends on the loop filter. Okay. So, for the frequency ramp, what you see is that it depends on what is the value of the loop filter at s equal to 0. Type 1 PLL. Okay. For type 1 PLL, loop filter of s is equal to 1 by 1 plus s tau 1. For type 2 PLL, loop filter is equal to 1 plus s tau p divided by s tau I. Okay. So, you can substitute for both the cases. What you are going to see is the following. For type 1 PLL, as s tends to 0, loop filter is actually, if you look at it, as s tends to 0 for loop filter, this is equal to loop filter of 0 is 1. For type 1 PLL, phi error of a steady state is equal to limit s tends to 0 times delta omega in 0 divided by s into kpd k VCO loop filter of 0 is 1, which is s goes to 0, this goes to infinity. So, if you have a type 1 PLL, okay, type 1 order 1, that is what we have been using, then when you apply a frequency ramp to the PLL, the steady state phase error goes to infinity, which means the phase error does not settle, the PLL loses log, it is not logged anymore. Okay. For type 2 PLL, phase error in steady state, its limit s tends to 0 delta omega in 0 divided by s times kpd k VCO into 1 plus s tau p divided by s tau I, s cancels out. Okay. What you see here is limit s tends to 0, this I am going to substitute now, delta omega in 0 divided by kpd k VCO into tau p by tau I, right. This is interesting that when you have a frequency ramp or the change in the input frequency is given as a frequency ramp, in type 1 PLL it will lose log, but in type 2 PLL you will have a fixed phase error given by this at the output of your phase error detector. Okay. So, this will be the fixed value which you have. So, we can just look at it here. For type 1 PLL, for phase step, you had 0 phase error. For and type 2 PLL, that also has 0 phase error, okay, whether it is type 1 or type 2. For frequency step, type 1 PLL has fixed phase error and type 2 PLL has 0 phase error. For frequency ramp, type 1 PLL loses log as the phase error tends to infinity, whereas type 2 PLL has fixed steady state phase error. So, looking at this trend, you may be tempted that if I want to make this steady state error equal to 0, then type 3 PLL may be a solution. You can increase one order of integrator. So, let us just take that example. Let us say for type 3 PLL, I can have my loop filter of S as 1 plus S tau P 1 into 1 plus S tau P 2 divided by S square tau I 1 and tau I 2. Right now, tau parameter, they are just constant. So, do not worry about it. What these values they will pick, we will see that during the implementation if required. Okay. So, for this particular loop filter, for frequency ramp, let us calculate the steady state phase error. So, this S tends to 0, we will use the simplified expression which was given here, right. You have delta omega in 0 divided by S times KPD KVCO, okay, into loop filter of S. So, I will put this as S tau P 1 into 1 plus S tau P 2 divided by S square tau P 1 and tau P 2. So, this goes off. What do you have in the end? You have S tends to 0, delta omega in 0 divided by KPD KVCO times 1 plus S tau P 1, 1 plus S tau P 2 into S, which is equal to 0. So, for type 3 PLL also, what you see is that even in the case of frequency ramp, right, your error is equal to 0. So, I will just summarize it. So, what you have is for we are going to write the steady state phase error for type 1, type 2 and type 3 PLLs. Okay. When you apply, we are going to write what is the steady state phase error for phase step, for frequency step and for frequency ramp. Okay. So, when you have phase step, type 1, type 2, type 3 PLL, they both all will give 0. When you have frequency step, type 1 will give you delta omega by KPD times KVCO. Okay. Type 2 PLL will give you 0, type 3 will also give you 0. When you have frequency ramp, type 1 PLL will give you steady state phase error as infinity, that means not locked. Type 2 PLL is going to give you KPD times KVCO, let us just cross check the value what we have, into tau P by tau I. Okay. Is it true? Okay. So, this is not tau P by tau I, because when you substitute S equal to 0, here this is 1, sorry. So, you have 1 by tau I. Okay. In the previous case, you substitute S equal to 0 in this case. Okay. Now, yes, right. Now, you go back and this is, we have to correct it, this is divided by tau I, and for frequency ramp type 3 PLL will still give you 0. So, based on what you would like to do with the PLL, whether you would like to apply phase step, frequency step or frequency ramp, you can choose the type of the PLL. Okay. And type and order of the PLL will depend on what kind of tracking do you want. So, based on that you make a choice. Then you may ask that okay, why I did not have only S square, why I needed to have S tau P1 and S tau P2. Similarly, for case of type 2 PLL, why I had S tau P. Well, all these things are required to stabilize the loop. We will see the stabilization in the upcoming sessions. Okay. Thank you.